Hello everyone. In this video I'm going to be specifically looking at ionic bonding. So what we mean by an ionic bond and the types of structures that we get this in. It's one of a sequence of videos that I'll be doing on bonding types found in chemistry at Key Stage 4. So in other videos I look at covalent structures and I'll talk about actual what are called giant covalent structures, and equally I'll do a separate video on giant ionic lattices. So more specifically to do with the structures you find this type of bonding in. But this video is just really an introduction to that. So I've got a sentence at the top saying a little bit about ionic bonding there, but the key thing is that ionic compounds are those that contain ions in them. And the ions come from reactions between a metal and a non-metal. Now that's key for ionic bonding because covalent is between non-metal and non-metal. So what we've got are metal and non-metal atoms essentially becoming ions. And between those ions we get what's called a strong electrostatic attraction, and it's that is ultimately our ionic bond. Now metal atoms typically lose electrons to gain a full outer shell, and they become positive metal ions, or cations as they're called. The non-metal atoms find it far easier to gain electrons to gain a full outer shell, and they become negative ions called anions. That's A-N-I-O-N-S. So they become anions. And not actually, just a little fact about anions, the name of the ion usually ends in ide, I-D-E. So if you see the term like chloride, iron oxide, nitride, that is usually the anion that they're referring to. So let's draw some structures and really put this into a kind of a context, give an example. So we'll start with a metal atom, and we'll talk about how a metal atom becomes a metal ion. So we'll use sodium as our example. So we've got sodium here. There's the center of a sodium atom, the nucleus, and if you look on the periodic table, you see the atomic number of sodium is 11. Now that gives you the number of protons within the nucleus, but also the number of electrons orbiting that nucleus. So we've got 11 electrons. Now it's not the best drawing, but we're going to just draw the shells, the orbitals around the center, and I'm going to use X's to represent electrons. So we have 2 on the inner shell, bit of a wonky circle there. We have 8 electrons on the next shell, and then what we find is that on the outermost shell of the sodium atom we have just 1 electron, and it's that electron ultimately that is going to be involved in this reaction, because it's far easier, you can see, to become stable for this sodium atom to lose that 1 electron, to lose this X, than it would be to gain another 7. Rather than gaining another 7 electrons, it's far easier to lose that 1. So let's just have a look at what we actually have in this sodium atom. Our proton number, so we've got proton number is 11, and that would actually be plus 11, because that's going to be a positive charge. In terms of electrons, we have minus 11 if we think of the charge there. So our total charge we consider charges, our total charge there is 0. Now when we write out what the electron arrangement is, because you may very well get asked to draw the electron arrangement or write the electron arrangement, we would write it like this: 2.8.1, and we can see that that is a partially full outer shell. So we've got here a partially full outer shell, and that's how we would write it, 2.8.1 for our electron arrangement. Now when that sodium atom loses the electron, essentially what we'd get is something that looks a bit like this. If I just draw an arrow over to the right hand side to just draw what we have now. So we put our sodium nucleus back in the middle, but now we have 2 electrons on the inner shell, 8 on the one around that, and that's it. Because we've got rid of the 1 electron of the outer shell, the outer shell goes. But what we need to do is add this on a diagram. It's a sort of big square brackets, because what we're saying is all of this ion now, remember we've gone from atom to ion because we've lost the electron. All of this ion now has a positive charge. So we draw it with a positive symbol next to it. So we'll draw a nice big positive symbol there above it. And if we were to consider the proton, electron and charge number this time, we'll see that our proton number is, again, if we just draw little arrows here, is 11. Our electron number now, because we've lost 1, is 10. So our overall charge is +1. And if we were to write out our electron arrangement, this would be 2.8. And we don't have a 1 now because we have a full outer shell. So again, what we could do is put brackets around this and represent it with a little plus on top. So what we've got there is a diagram of the sodium atom on the left, the diagram of the sodium ion on the right, and we've shown the electron arrangements. Now what I'm going to do is essentially show you what happens to the metal atom becoming an ion, show you how a non-metal atom becomes a non-metal ion, and then I will explain how you can represent the ionic bond forming between the two. So we said that metal atoms lose electrons to become metal ions, but in an ionic reaction, to form an ionic bond, non-metal atoms become non-metal ions, and they find it easier to gain electrons. So what we'll do is we'll just shrink the screen a little. We'll move this up here, just so I can continue by explaining, and I use sulfur as an example here. Sulfur, I won't necessarily do the proton, electron and charge bit, I'll just explain it quite simply. But if we consider sulfur this time as a non-metal, so we've got the center of a sulfur atom here. Now sulfur has 16 electrons in total, which means it would have 2 on the innermost shell, 8 around that, 2, 3, 4, 5, 6, 7, 8, and then 6 on the shell around that. 1, 2, 3, 4, 5, 6. So let's just put in our electron arrangement here. What we essentially have is 2.8.6. We can see we've still got a partially full outer shell. But rather than losing 6 electrons, it's far easier to become stable by gaining 2 electrons, because what we're looking for is this atom to become stable. They're looking for this stability, and it comes from a full outer shell. And we get that full outer shell by having 8 electrons in it. So this sulfur atom essentially will become, just draw this over to the side, a sulfur ion, where we'll have our sulfur nucleus in the center. We're going to have 2 electrons here, followed by our 8, 1, 2, 3, 4, 5, 6, 7, 8. And this time again, 1, 2, 3, 4, 5, 6. But we're essentially going to be gaining 2 electrons when the sulfur atom becomes a sulfur ion. In that case, we're going to need the brackets again. So we can put our brackets around here. And because we've gained 2 electrons, we're going to have a 2 negative charge. Not a -2, but a 2 minus charge over the square bracket. So our electron configuration this time can be 2.8.8. And we can put brackets and a 2 minus over that. And what we've got there, when the sulfur atom gains 2 electrons, it becomes a sulfur or sulfide ion. Now what I've done is show in this video the principle between getting from a metal atom to a metal cation and a non-metal atom to a non-metal anion. But what you'll be asked in an exam question is how to represent essentially a reaction between these two. And all you essentially do is draw what I've kind of drawn here, and you just draw an arrow to represent the movement of the electrons. So what I'll do is shrink the screen one further time. We'll just move this up here. And I'm going to now show you the reaction between, rather than sodium and the sulfur, I'm going to do a typical one that you get in exam questions, between sodium and chlorine. The reason why I wanted to use sulfur as an example of the non-metal was just to show the difference between having a +1 charge and a 2- charge, because you change the number depending on how many electrons are transferred. But as a full example, I'm going to talk you through the reaction between a sodium atom and a chlorine atom. So let's go from the top, and we'll put in at the bottom here Na, and we've said that there were 2 around the outside, then 8, 2, 3, 4, 5, 6, 7, 8, and then a final shell. We said that shell had just 1 electron. Now chlorine, if we were to look at chlorine as a non-metal atom, you can see that that actually has 2. If we draw the electron arrangement there for chlorine, chlorine has 2 in the innermost shell, 8 on the one around that, and on its outer shell it has 7. So its atomic number is 17. Now clearly you might be able to see that sodium wants to lose this electron, and chlorine ideally would want to gain 1 here. So you can represent this reaction in an exam question by showing the movement of the electron to its new location. So in this reaction between a sodium atom and a chlorine atom, you simply just show an arrow to represent the movement of the electron you want to represent. And then you can show the reaction in terms of the actual ions that you produce. So in the end, what we'll end up with is something that looks like this. Sodium with 2, apologies, not the best drawing, but 2 and then 8. And remember, we can put the brackets around because this is a plus. And next to that, we can have our chlorine that has 2, 8, and now a full outer shell of 8 electrons. And once again, we put brackets around that with a negative to represent the negative ion there. And that very simply is how you represent an ionic reaction in an exam question on a diagram. So I started by just introducing the topic, and then I've got how you would show the metal atom becoming a metal cation and the non-metal atom becoming the negative anion. And then at the bottom here, just for the last few minutes, all I've done is just really show how you represent this in a schematic diagram, showing the movement of the electron, hence the green arrow that I've drawn on the left-hand side of the video. And then we can represent the 2 ions that you get. So clearly we've had a sodium atom reacting with a chlorine atom to form essentially this thing on the right, which is sodium chloride, or NaCl. Now, just one final point to say is that the inner electron shells can sometimes be left out of electron diagrams because actually they're not involved in the bonding. So what I mean by that is, for the sodium atom, if you take, for example, on the left-hand side of this video, I could have just drawn one outer shell around it and just had the one electron on that. I didn't essentially need to draw the inner shell of 2 and then the next inner layer of or layer around that of 8. Sometimes in exam questions they just simply draw the outermost shell, and that's one way just to really speed up your answer. So if you wanted to do that, you could just draw a sodium atom again with the 1, and you could have the chlorine atom with the 7 electrons, and equally when you draw the ions you can just represent the full outer shell there. But there you have a little bit about ionic bonding. So an ionic bond is formed from a reaction between a metal and a non-metal. And when you get a metal and non-metal ion reacting, you get a strong electrostatic attraction. It's that is the ionic bond. And you can represent that in a diagram with these brackets and relevant charges on them. Okay, hope all that helps.